A boat leaves a dock to cross a river at a bearing of south 68 degrees east. The boat is traveling at 17 miles per hour relative to the water, and the current is flowing due east at 6 miles per hour. We're going to find the boat's true speed and bearing. All right, so first of all, the boat is headed measuring off from south 68 degrees to the east. So there's a vector representing the boat, and it's going 17 miles per hour. Now the river is flowing due east at 6 miles per hour. So there's our two vectors, and if we added those two vectors together, we could move this down here so we could see it geometrically. And what we want to find is the boat's true speed and direction, which would be this one. Now you can solve this with law of cosines, or you can solve this by writing the vectors in component form and adding them together. I'm going to write the vectors in component form and add them together in this video. If you want to see it solved with the law of cosines, then watch the other video. Okay, so let's go ahead and express our vectors. We've got a vector for the boat, and the vector for the boat, if we look at, we need the components, it would be 17. For the x component, it would be cosine of the angle. Now, not the bearing angle, 68, but the angle measured off from 0, so it would be this angle right here. But we can see how we can get that, because all the way around to our horizontal line is 270, and if we add the 68 to that, we get 338. That is our direction angle for our vector. The second component then would be 17 sine of the 338. Okay, so now let's go ahead and express a vector for the river. So the river vector will be, it's going at 6 cosine, well, this one is right along the positive direction, the x-axis there, so that's just going to be 0, and then 6 sine of 0. Now to get our red vector, or our resultant vector, we need to add those two together. I'm just going to use a capital R for the resultant vector. It's going to be the sum of the other two. We're going to add them component wise. So we're going to have 17 cosine 338 degrees plus cosine of 0 is 1, so that's just going to be plus 6. Second component's sine 17 sine 338 degrees, and sine of 0 is 0, so that's all there's going to be on that one. Okay, so to find the speed of the boat, that's going to be the magnitude of the resultant vector. So it's going to be the square root of, let's go ahead and put these in a calculator. So we got 17 cosine 338 plus the 6, and we're going to carry it to a couple places. So this is 21.76 about, and then we've got 17 sine of 338, and that is negative 6.37 approximately. So we're going to take those values and we're going to square them and add them together and square root them so we can find the magnitude of the vector, 6.37 squared. And it looks like I get 22. We're going to carry it to a couple places here, 6, 7. Now if we were to answer this, it says nearest mile per hour, so we'd say 23 miles per hour. Okay, now we need to find the direction, and we're going to be measuring off south, swinging around here to the west by that angle right there. So if we find the direction angle for the vector, we're going to have to do some modification. So let's go ahead and find that direction angle first. So it's going to be the inverse tangent of the y component, negative 6.37, over the x component, 21.76. Now we know if we do inverse tangent of a negative angle, the calculator is going to give us an angle in quadrant 4 measured as a negative. So it'll give us this little angle right here. And once we have that little angle, then we'll be able to get at what we need for the bearing angle. So we're going to do inverse tangent of negative 6.37 divided by 21.76, and I get negative 16 16.32 degrees. Okay, well, that's measuring off the negative, but the size of that angle is 16.32. Okay, now I can see how I can get at my direction angle, because that 16.32 and the direction angle add up to 90. So I just need to do 90 minus the 16.32, and I'm going to be measuring off south, and I get 73.7 degrees to the west.